we're going to take a look at an application for derivatives, and that application is about projectile motion. So the first thing we need to do is define our position function, or the function that's going to tell us the height of the object at any moment in time. That function is s of t. So s stands for position, t is time. So this is function notation s of t. S of t is equal to negative 16 t squared plus the initial velocity, v0, times time, plus s0, which is the initial height or the initial position. Okay, so these subscripts of 0 tell you that it's the initial or starting velocity or initial or starting position. The negative 16t squared comes from acceleration due to gravity being negative 32 feet per second squared, and it's actually half of that. Okay, so we're going to do all of this in feet per second or units of feet. All right, so a rock is dropped from the top of a 400-foot tall cliff. So that 400 feet, that is our initial position or our initial height. That's our S0. Since it was dropped, that tells me that the initial velocity is 0 feet per second. All right. So what we want to do is we want to find the average velocity over the time interval from 1 second to 2 seconds. All right. Average goes along with a secant line. All right. If you think about finding velocity, velocity or speed is a change in distance or position over a change in time. So that means I need to use the distance formula or the position function. Okay, so to find average velocity over an interval, we are going to do s of b minus s of a over b minus a. So it's just like the slope of a secant line. All right, so for this particular example, we're going to do s of 2 minus s of 1 over 2 minus 1. S of 2. So what's our s function? So we should go back and write that s of t for this problem is negative 16t squared plus 400. The VOT disappears because the initial velocity is 0 because the object is being dropped, and the initial height is 400 feet because of the 400-foot tall cliff. So that is our position function. So now when I plug 2 into that, I'm going to end up getting negative 16 times 2 squared plus 400. That is s of 2. I have to subtract s of 1. That will be negative 16 times 1 squared plus 400. This is all divided by 2 minus 1, which is just 1. Okay, so negative 16 times 2 squared, that's negative 16 times 4, which is negative 64. So we have negative 64 plus 400 minus, and then we have negative 16 times 1 squared. Well, that's negative 16, so it'll be minus negative 16, so plus 16. And then minus 400. So the 400s are going to disappear. This is all being divided by 1. So this is really, if I go through, I can cancel off these 400s. Negative 64 plus 16 is negative 48. So our answer is negative 48 feet per second. Since it's an application problem, I should have units in my answer. Since I'm talking about velocity, I'm talking about feet, this is in feet per second. Okay, so that's to find the average velocity. The question now becomes, how do I find instantaneous velocity? So what's the velocity of the rock 2 seconds after it is dropped? If there's only one time given, that means I need instantaneous rate of change. Since I need an instantaneous rate of change, that means I need a derivative. So there's a rule that says the velocity function is equal to the derivative of the position function. All right, again, our position function for this problem was negative 16t squared plus 400. I want the derivative of that, so I do it using the power rule. That'll be negative 16 times. The derivative of t squared will be 2t to the first, plus the derivative of 400, which is 0. So our velocity function, which is the derivative of our position function, is really just negative 32t. If I want to know the velocity exactly 2 seconds later, I just need to know, well, what is v of 2? Or what is s prime of 2? Well, that's just negative 32 times 2, which is negative 64 feet per second. All right. So to find velocity at one moment in time, that means I need to do instantaneous, I need a derivative. If I want to do average velocity, I need to use the position function. That's it.